Our universe started with the Big Bang. Or did it? Let's see how far back in time we can push our certainty, and let's see what questions still lie beyond the limit of our understanding. The Big Bang Theory was pretty contentious when it was first proposed, as is any picture of reality that conflicts with the current dogma. And I'm talking about both scientific and religious dogmas of the time. However, these days there's really no doubt that at some level, the Big Bang Theory gives an accurate description of the earliest epochs of this universe. But how accurate? What parts of this story are we absolutely sure about, and what parts are still genuinely in question? Today, we're going to talk about the evidence that gives us so much certainty for parts of the theory. We'll follow with an episode describing which bits are still highly uncertain, and possibly even just plain wrong. I'm not going to spend a lot of time describing the theory. There are so many great resources for that, and we've linked some in the description. Just the basics. The Big Bang Theory is a set of descriptions detailing the expansion of our universe from a tiny, super dense, super hot speck to the enormous cosmos that we know today. These descriptions are in the mathematical language of physics, and they build on and are supported by many experiments, from astronomical observations to particle collider experiments to supercomputer simulations. Some of these experiments have verified certain parts of the theory beyond reasonable doubt, while other parts remain untested. Let's start with the irrefutable. The universe is expanding. Light from distant galaxies is redshifted, stretched to longer wavelengths, and the further away the galaxy is, the more its light is stretched. In the context of Einstein's theory of general relativity, the only sensible interpretation for this fact is that space itself is expanding, and light travelling through expanding space is stretched. The more distance travelled, the more it's stretched. The universe is definitely expanding now, and so we know that once upon a time it had to be much smaller. See, this is the wonder of physics. We can look at the current state of the universe, or even just a tiny part of the universe, and run the laws of physics forward in time to predict the future, or run those laws backwards and predict the past. If we rewind the universe using the mathematics of general relativity, then the further back you go, the smaller the universe is. In fact, with raw general relativity, we get that the entire observable universe was once compacted into an infinitesimal point, a singularity, at time t equals 0, the hypothetical instant of the Big Bang. Now, that initial singularity is not something that most cosmologists believe in. While general relativity is incredibly successful, it doesn't contain the machinery to describe the quantum scale gravity of that first speck. So, we know that at some point in our rewind, pure general relativity will give us the wrong predictions for the behaviour of space-time. But we understand those limitations really well, and we know that we can be confident in our predictions down to a certain point. For times after that point, our understanding is good enough to make some pretty bold and testable predictions about what the universe must have looked like at various times. One such prediction is that the entire universe was once as hot and dense and opaque as the inside of a star. It was a searing ocean of protons and electrons, a plasma. As the universe expanded, this plasma cooled, and at a very particular moment, when the universe was around 400,000 years old and about 1,000 times smaller than it is today, it hit a critical temperature of 3,000 degrees Kelvin, at which point the entire universe slipped from plasma to gas as the first hydrogen atoms formed. In the same moment, the infrared light that had previously been trapped in this fog was free to travel the width of the cosmos. It's still traveling today, carrying with it an image of that early time, and we see it. It's no longer infrared, having been stretched into microwaves as it traveled through an expanding universe. It's the cosmic microwave background. We talk about it in a lot of detail in this previous episode. So here, I just want to emphasize that this ubiquitous radiation is almost impossible to explain without a universe that was once much smaller, hotter, and denser. So at least that far back in time, the Big Bang Theory is right. We see some amazing clues in the image imprinted on the CMB. Firstly, it's incredibly smooth and even, but this mottled pattern shows there are imperfections, tiny differences in temperature of 1 part in 100,000 from one patch to the next. These represent regions where there's a bit more stuff here, a bit less stuff there, very, very tiny fluctuations that would later collapse on themselves to form galaxies and clusters of galaxies. That process, the evolution from a smattering of tiny fluctuations to a network of giant galaxy clusters, is also evidence that the Big Bang picture is right. When we look to vast distances, we're also looking back in time, and we see the very first galaxies soon after they collapsed from these blobs. Now, we expect them to be violent places, with galaxies colliding and merging with each other, rich in the raw materials of star formation, but poor in the heavy elements released by generations of supernovae. And they are. We see galaxies back when the universe was 5% its current age, and they look very different to galaxies today. The universe is clearly evolving. But there's another amazing clue in the CMB. We see ripples of sound waves in the pattern of those fluctuations. The fancy name is baryon acoustic oscillations, which cause ring-like clustering of the CMB fluctuations. If the Big Bang theory is right, then those ripples should have been frozen into the distribution of matter at the moment the CMB was created. And those ripples should still be visible in the way that galaxies are spread out on the sky. And yup, we see that too. But all of this only gets us back to 400,000 years after the Big Bang. We can rewind further. At an age of a few seconds, we predict that all of the universe was much hotter than the very center of a star, and remained so for around 20 minutes. During this time, nuclear fusion raged across the cosmos, baking some of the existing protons into heavier elements in a process that we call primordial nucleosynthesis. The Big Bang theory tells us how long these elements were baked and at what temperature, and so predicts the proportions of deuterium, helium, and lithium that should have been produced. It's in startling agreement with what we see when we look out there. The Big Bang theory has powerful, direct evidence, almost down to the first second. Although we don't have direct evidence for what the universe looked like in its very first second, our understanding of physics is still good down to a crazily early age of 10 to the power of minus 32 seconds, when the entire currently observable universe was around the size of a grain of sand, give or take. How can we be so confident? Because we've recreated the conditions of the universe at this time. We've recreated those insane energies in our particle accelerators. We can check that our physics works in these conditions, and so we have a lot of confidence in the predictions of that physics. However, this is where our certainty ends. Earlier than 10 to the power of minus 32 seconds, we just can't produce the energies needed to test our understanding of physics in those conditions. But there are clues to that earliest of times. Some are also imprinted in the cosmic microwave background, and they may lead us back to the instant of the Big Bang itself. We'll rewind to the very beginning of space-time on the next episode of Space-Time. A couple of weeks ago, the LIGO team announced the very first detection of gravitational waves. We did an episode, and you guys were all over it. Brendan Binns asks, given this detection, is the theory of general relativity still just a theory? Well, actually, it's even more solidly a theory than ever. In science, when we say theory, we mean a description of reality that has stood up to many, many experiments. We only call it a theory if we're pretty much certain that the basic picture is correct. Theories actually contain laws, and those laws are often the most well-established parts of a theory. A theory may still have parts that aren't so well established, but such uncertainties don't invalidate the overall picture. If they did, then we wouldn't be calling it a theory. David Mulick points out that it's kinda weird that advanced LIGO was turned on just in time to catch the gravitational waves from the merger of black holes. Very insightful. that almost as soon as LIGO became sensitive enough to spot black hole mergers, it spotted one. If these events were rare, then yeah, it'd be pretty weird. But what if they happen every few weeks? That's actually the frequency of detectable mergers predicted by some astrophysical models. And that's about at the midpoint between conservative and optimistic. If accurate, then we'd expect to see one pretty soon after reaching the necessary sensitivity, which we did. But that was months ago. Shouldn't we then keep seeing them? Shouldn't we have seen several by now? LIGO's press release was about the first detection. They didn't say anything about whether there'd been others. There have, but LIGO remains cautious and is giving each detection due care. John Proctor points out that the date cited for the discovery of this black hole merger is September 14th, and yet the official turn-on date for advanced LIGO was September 18th. As we mentioned in our earlier video, right after the first detection, the rumour at the time was that the detection was in the engineering data. There were 8 test engineering runs before the official turn-on, with the sensitivity improving each time as more and more of the upgrades came online. The 8th run was at full sensitivity, right before the official turn-on. That's when this merger was seen, as soon as LIGO had fully leveled up to the point that was actually capable of seeing them. To quote Lawrence Stanley, "Okay, but until the discovery of gravitational waves can lower my mortgage and reduce the price of gas at the pump, it remains just a song that nerds sing to put their kids to bed at night." In other words, so what? It doesn't mean anything to anyone in the real world. But what a beautiful song. I'll be humming it to myself with the other nerds, as these observations grant us stunning insights into the fundamental nature of space-time. I'll still appreciate the impractical beauty after those insights allow me to ride my inflaton-powered anti-gravity warp ship to the stars. At that point, I won't be so worried about the price of gas.